And start at one end and work your way through. Or possibly middle if sorted. We call our binary search. All right, with a graph, isn't exactly an end to choose from. So we'll start somewhere. And the trick is to not get stuck in a loop. All right, since our graphs are going to have cycles in them. Well, two ways we'll talk about searching: breadth first search and depth first search. So with breadth first search, starting at a vertex, we'll NQ the neighbors that vertex that have not been marked as enqueued before. Then we'll pull from the queue and repeat the process until the queue is empty and all vertices have been processed. All right, so initial state we'll put that first vertex onto the queue. So we'll need a good old graph, and then we can process it from various starting points. All right, just an arbitrary general graph. No particular shape to it, simple graph. So if we're starting at vertex A, go ahead and NQ A. We'll DQ. Give us back A. All right, so my Q state. Q state like such, presently empty. It has two neighbors, B and F, and we'll NQ them in that order. You remember this data structure is being represented as a matrix or list, and whether it's matrix or list, we maintain this data alphabetical order. So our Q state is now B and F. So let's go ahead and mark that. And so we started at A, and we went ahead and processed that B and F are places that we can go to. DQ pulls out B, Q state, just F, and we'll look and see what Let's see. Let's get these side by side. All right, so we have A processed, B and F information that we noted. And now we're going to go ahead and process B. Go ahead and NQ. All right, so B has A, C, and E as neighbors. A has already previously been notated. So we'll just NQ, C and E. So our Q state is F, C, and E. All right, so we know about C and we know E, and then we'll go ahead and dequeue again. Dequeue pulls the first value off. And it's a vertex that we've searched before. Q state C and E. And keep on going through. So process F tells us about G. So our Q state becomes C, E, and G. Learned about one extra data point. Everyone still with me so far? Working our way through. A, B, and F we've actually visited. C, E, and G waiting in line. DQ, pull the first one off. Take Q state, E and G. Process C, processing C tells us about D. Updated Q state, E, G, and D. Carry along, DQ, pulls out E. All right, tells us about D and H. All right, tells us about D and H. D has previously been noted. So all we need to do is add H to the end. What are we searching for? So typically we're searching for ourself. See if there's a way that we can go ahead and get back to ourself, basically identifying that there's a loop. Sometimes we might just be searching for another vertex, or we might be just searching for paths that we can build from that starting vertex to all other vertices. All right, so we're in the general form of just searching out all the vertices. So we don't have an early exit condition here, but being able to work our way back to ourself is typically what the searches are used for. The other thing is we do is search for connectivity to see if there's connectivity between a vertex and another vertex based on that graph or subgraph that we are processing. All right, so we processed, did our NQing, I'm going DQ, get G out. G is going to tell us about H. Nothing that we didn't already know about. I sent the link to one person. Okay, look at that. Sorry, everyone. Here's the link to the page. Full joinings. I managed to send it to one person. Yeah, right now we're in the general form, so we'll just keep dequeuing in while there's a queue that still remains to be processed. Processing G tells us about H, right, which is not new information. All right, so our queue state does not change. And we can dequeue. Pull D out. H remains on the queue, process. Processing D tells us about I. So our queue shall grow. HI, dequeue. Pulls H out, which gives us no new information as we process it. Process H yields nothing. dequeue. Get myself thinking about Dairy Queen with my typo there. Queue state is back to empty. Process I yields no new information. And everything is done. So order of processed nodes. We had A to start. Where do we go next? A, dequeued B, dequeued F, A, B, F, C, E, G, C, E, G, dequeues, D, H, T, H, I, anybody here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Everyone's there. Okay. Oh, yes. Searching graphs, most definitely. Thank you. I got a little bit too specific there since a tree is also a graph, but we're being a little bit more generic there, aren't we? And so the idea why it's called breadth first search, we're just trying to stick as close to A as possible. A was 0 away. Then we had B and F at 1 hop from A. Then we had C, E, and G at 2 hops from A. Then we had D and H at 3 hops. And I at 4 hops. 1, 2, 3, 4. Right from A. Right, so the order processing is basically creating more like levels. Effectively, what we have here is a tree for the way that we did grow things. So turning the graph into a tree, that's one of the things that can be done. These effectively are levels of that tree. All right, so we have where we have A at the root, B and F. So we turn in a tree. Sometimes a tree is useful. All right, F gave us G. B gave us C and E. And where did we go there? F. C gave us D, right? Processing C. C gave us D. What else do we have here? E gave us D and E gave us H. And D gave us I, right? It's not very exciting tree, but you can see the levels: 1 hop away, 2 hops away, 3 hops away, and then 4 hops away, way down here at the bottom. Right, so we go hop A, B, C, D, I, A, B, C, D, I to get I. Not, of course, not the only path there, but right, we just happen to create a subgraph. On this graph, and that subgraph just being a tree on the graph. Let me go grab. Let's just screenshot that. Grab the link. Let's see. All right, we'll look at their example in a second here. We'll do another one. All right, so this one's on a tree, so that one's less exciting. Let's go to one. This may not be the link I was looking for. Interesting. All right, so tree building is one of the things we can do here. It's interesting. This well, okay, they're using a tree here, flat out here. It used to be a graph that almost looks like a tree, but there was a back edge going from, I think it was like 10 over here to 3. It seems they have changed, where somebody changed things a little bit here. So I guess we won't do that particular. You see they went and took their map of cities and then we could turn it into our tree. Same idea. All right, good old notation, multivariate, of course. And let's do, oops, another example. Find the page, I'm on the page. Okay. And it's depending on where we start. We'll get a different tree and different traversal. All right, so I'll just keep the queue up here. And if we go ahead and start at D. And queuing, starting at D, we would get CEI on the queue. We would dequeue, right? So it's going to draw. We process D and found out about those 3 neighbors. C was first up, so we'll pull C off. And it will tell us about B. Then we'll pull E off. That leaves I and B. Pulling E off also tells us about B, but we already know about B. But H is new information. All right, so we don't care about that edge there. It's not relevant since we already knew about it. Pull I off. Pulling I off tells us about no one new. So we'll go ahead and pull B off. Use down to just H. This will tell us about A. Let's see, by pulling off, yes, by dequeuing. All right, because it's a queue. Pulling off is a dequeue operation. All right, we know about A. All right, so basically we got two possible branches that we're building in our little tree here. Since H showed up first, H gets pulled off first from the queue. And it tells us about G. A is out next, which does tell us about F. Pull out G. Doesn't give us any information. And then we pull out F. And down in empty state. And again, it does form a tree, the root just being where we happen to start. But more typical search is going to be a depth first search, DFS. All right, so here starting from a vertex, we'll go to the first unknown or unvisited neighbor. And from there, we'll repeat the process. All right, so starting from A, we have two options, B and F. As before, we will be using the first one that we can go to. All right, so we chose B. All right, so from B, we have C and D to choose from. And then we'll choose C. Just work our way down. I guess I have arrows here, might as well use them. And we'll just keep on going. All right, so from C, we have only one choice. A single choice. Going to D, right? Because we've already been to B. Two options again here, right? E or I. From D, E or I. And we'll choose E. All right, from E, just have H as an option. So we'll go ahead and choose that. And then we have single options here again until we get to F. And so we go to H, go to G, go to F, and we've hit a dead end. Or looking at it from cycle detection. We found A again. But we want to go ahead and get through everything. So what we're going to do is backtrack. Backtrack from where we came. Looking for a road untraveled. We'll talk about endpoints after this, which is another place where backtracking in general, various puzzle solving techniques are going to involve ourselves with backtracking. So we go back to G. If there was a neighbor here that we had not yet been to, we'd go and visit it. There's not, so we'll go ahead and go back to where we came. Same story at H, same story at E, digging our way back. And then we found another road, right? So we backtracked all the way to I, or D, and then got ourselves to I. So we backtracked all the way to D, finding another road travel. Then we'll backtrack again from I. This will get us back to A, as we've been everywhere. Let's see. I can get my arrows lined back up here. Okay. Work our way back. Back to D, no other options. Back to C, no other options. Same story with B, same story with A. And we made it back to where we started, and there aren't any new paths available to us from there. Okay, I was thinking depth research earlier. All right. All right, same idea here. This is a graph. This graph almost is a tree, except for this or this edge. Either the BF or the EF edge would need to be removed, and then it wouldn't be a tree. But all right, starting at A. Right here, they're saying left to right, which yes, because the matrix would be A. A has a neighbor of B, C, and E, and we go from left to right in an underlying matrix. All right, so A goes to B, then D, come back. F takes E, dead end, work our way back, then ACG. So let's draw that out, right? Let's get my colors. Consistent. Go forward, we go forward until there is no more forward. So we go back, go forward, and then work our way back until we come to a place where we have another way forward to C to G, and then back again to where we began, and we have no other roads to travel. And so ABD, FE, CG. ABD, FE, CG. All right, so all kinds of good stuff here to keep reading on as well. Yeah, the code, there's nothing terribly complex about the code. All right, yeah, lovely stack going on here to keep track of things because they did it iteratively. This is where recursion is helpful. It uses the stack for us to keep track of where we are. So basically, started a node, and then we just go ahead, once we find a node to go to, we just make the call again from there. And the key thing is, right, they're calling here labeled, known, unknown, right? Various many ways to mark a node such that we know it is not going to cause us to go in a loop. And probably just using a hash map for that, which is one of the topics we're getting into, not too distant future. Let's do another example just to make sure. All right, so I'll do the arrows second. So we'll go ahead and start at E. All right, so we got E on our output. And our next option is choice between B, D, and H. Which shall we go to? B, D, or H? Who's first? Got to vote for H. It's an option. Are we arbitrarily choosing amongst the options that are presented to us, or are we doing it algorithmically? So H is not the option we're going to choose.
Are you trying to get to A? Is that what you're trying to do? Or get to I?
We're not trying to get to anywhere.
Okay.
We are just digging around. In the case of E, we'd be trying to dig for ourselves. All right, so we got other letters to vote for: B, D, or H. Okay, let's circle back. Let's forget there's an image
Well, B.
altogether. And I've got to vote for B. 2 votes for B. Let's go back to our matrix. 9. Vertices. It's a good size matrix. Not a very well connected matrix, but it is quite numerous. All right, A has B and F. B has ACE, ACE, C has BD, D has, we have here CI, CEI, E has BD, and H, F has A, and G. And G, where are we? G has F and H. H has EG, H, EG, and I just has D there. All right, so we do things correctly. Nice mirror image here. It kind of looks like a plane. Anyways. All right, so where we start, it's going to be arbitrary. It'll just be a given. All right, so we started at E. And E says, let's go ahead and go to the first vertex that we can go to, that we haven't been to before, right? So we can mark things here, just mark it bold. E is somewhere we've been, and the first option we had to do is B. So go here and go over to B. And then from there, in fact, let me get my colors fixed before we go too far. It's weird. Okay. E went to B. B is going to go to A. I'm going to mark A as bold. Then we go from there to where we go. We'll skip over B because we have already been there. Next up, we have F. So mark F as bold. F will then try. All right, A is no good. G we have not been to before. So we can mark that as bold. G, can't go to F, but we can go to H. And H sees we have E, but E is bold, so we don't go there. We have G. That's also bold. So it processes the list and finds that there's no one to go to. So we will have to go ahead and backtrack. Go back to whoever brought us here, which was G. At that point, it attempts to continue on, but there's no one beyond. So we'll go ahead and just draw that there is nowhere further to go from this point. So we'll go ahead and have to backtrack. And we get the G from F. So we backtrack. Looks for another road, doesn't find anything. We got F from A. So backtrack. F, A. It tries to find somewhere else. It does not. And we get to A from B. And then it goes ahead and pushes forward, getting us to C. Mark that. All right, B is bolded, D is not. So we can go ahead and go to D. And from here, C is bolded, E is bolded, I is not bolded. So go ahead and get to I. And we're back to the end of the line here. Already been to D, already been to everywhere. At this point, the algorithm could go ahead and stop since everything is marked. So no real reason to backtrack too much, but we'll go ahead and do it just be complete. All right, and we got to I from D. Go back, find the end, got a D from C. So we have to go back. The arrow party grows, and nowhere else to go there, and got to C from B. Nowhere else to go from here that we haven't already been. And the line takes us back to where we started. Back to E, and then we'll see, now we're back to where we started. We've got nowhere else to go. All right, so I don't even have to give you an image on the test to process the graph. But starting E, we went to B. We had choice between A and C. No choice, we go to F. No choice, go to G. No choice, go to H. E is a dead end. So we found our cycle. All right, so if all we're doing is a search for ourselves, so if we do search for ourselves, which vertices would be processed? It would be B, A, F, G, and H. Because we can go ahead and get to E at this point. Otherwise, we'll backtrack from that dead end. Gets us to C, to D, to I, and then we backtrack from there. All right, so this were a test question asking for full depth first search. right, from E, answer is this, sans that extra E, 'cause that would just be the cycle detection part. Asking it to search for itself from E, the process nodes. Right, or that first chunk. Does the data processing kind of make sense?
I have a question.
Yep.
How do we know from after H, it has to go back up to E row?
All right, so if I were to do the processing, we processed this way, and then we got a dead end. We can't go to E because we've already processed E. So at that point, we then backtrack, go back looking for other branches. When we get back to B, we find there is one. And we go this way. And then we work our way back to where we started. All right. This drawing is effectively the same thing as what we have here in the matrix.
So does that mean if you go back to where you started, you have to backtrack?
Yeah, if you get to the point where you can't get to a new vertex somewhere you haven't already been, then you backtrack. Right, and we could do the same type of searching on trees if we wanted to. This tends to be very uninteresting since there aren't any cycles. And pretty much depth first search pretty much ends up being a pre-order traversal. You go left, keep going left, and then you backtrack, right? So just like with a binary tree, if we just keep going left, when we get to a leaf, there's nowhere to go. So we go back to the parent. If there was a child on the other side, go ahead and we go that way and keep going down that subtree as far as we can until we hit an end, and then we backtrack. Okay, it's the same idea here. So talking about backtracking. Okay. All right, so backtracking is the concept of retracing your footsteps and then going back to a place where you made a branching decision and choosing different path from that point. And so in Queens, this is a backtracking problem where we look trying to solve a chessboard that is n by n, where we can place n queens on the board in a fashion such that no queen can capture another queen. All right, so board does require being 4 by 4, larger. Find a solution right? Not counting a 1x1 board, in which case, yeah, just one queen. There are no other queens to capture, so that's not queen, no queen. All right, so the way we'll solve this, working column by column, we'll drop a queen, the first available position. Then check that the placement is valid. Not, choose a different path. If we get stuck, we'll pick up the last queen placed and try again. All right, so see if we can't make a board here. Doesn't look too terrible. All right. I wonder, what are my background feeling? Try again. Correct button and things will work better. All right. We'll build a few states here. All right, so initially we'll go ahead and try to drop a queen. At this position, if you're not familiar with chess, the queen's the most powerful piece. Go ahead and move as far horizontally as she wants, as far vertically as she wants, as well as diagonally. And so all of those positions are not valid places to drop a queen. So that's why we're going to go column by column, because there is no other valid place in this column to place the queens. So we'll try over in the next column over. This doesn't work because it conflicts with the first queen. That doesn't work. Conflicts with the first queen. So go ahead and drop here. All right, so moving along. We're at this state. Go ahead and try to place a queen. Doesn't work. Doesn't work. And doesn't work. So we already hit our first dead end. All right, so what we're going to be doing from that dead end, I guess yeah, so there's our dead end. We'll pick up the last place queen and try a new location. Doesn't work. That does work. So we go ahead and keep processing. And we hit another dead end. So this last queen we'll pick up. Can't put it here, can't put it here. So we'll go ahead and do is go back, pick that up. All the options were exhausted there. And we went all the way back to our very first decision, said, that's not going to fly. So we'll keep on building, placing a piece, and then placing a piece. And we found a solution. There are lots of solutions. Once we found a solution, we can also then backtrack. So we go ahead and mark that. First solution found. So we'll pick up and try to find other places. All right, can't drop the queen here, so we're back to the previous decision. Try the next, doesn't work. Nope, nope. All right, back to the previous decision, which brings us all the way back to there, and we'll try this position. Moving along, dropping the queens onto the board, and we have our mirror solution found. All right, so now what we can do is go to a 5x5 board. As the board gets larger and larger, we're going to be running into a non-polynomial time problem space. Right, where it gets become quite significant. Problems. Right, good old NP complete. Basically, an NP complete problem is a problem that's so ridiculously bad that there's basically no good solution that can solve a problem of any size in a realistic time frame. So yeah, back when I was in college, close to a couple of decades ago now, I guess, and I wrote a program to see how big of a board, a chessboard, I can get. I just have a run, right? So does a 4x4 board, it's fast, 5x5, still pretty fast, and seconds start becoming minutes very quickly, minutes start becoming hours very quickly. And I think it was maybe somewhere between 18 and 21 queens that I got to letting the computer just run overnight. Right? So it just started becoming hours to find all the solutions to this problem. It's very, very time consuming. And there aren't very many NP complete problems out there. Right? There's a few different variations of NP, whatever, just non-deterministic polynomial time. If we were to put it on a chart, it would just basically be like a vertical straight line. And here it talks about the various types of NP complete, NP hard, all fun stuff. We're not getting into the fine details of all that fun stuff. And the lovely $1 million prize to do proofs. It's been a few years since this has been won. And if I recall correctly, the researcher turned the $1 million down. Must have been already won the lottery previously or something like that to turn down $1 million, because I'd have to find some sort of crazy strings attached to someone offering me $1 million. I would say no. Anyways. All right, so we got to go back. Same sort of thing when like doing maze solving, right? As we can go ahead and build, as we get to bigger and bigger boards, finding solutions becomes fairly easy. We found our first solution, backtrack back out, find a new position to put the queen, and we can keep building from there, right? So this one had to get picked up. That one didn't have an alternative, so that one gets picked up. And we move the queen down and see if we can solve differently. All right, now the solution, just kept digging down, same algorithm, dead end, backtrack up, and keep looking for additional solutions. All right, we're still on the board where the queen's just in the first position, but there we had a dead end. We couldn't find a solution. Back it up, try the next spot. All right, that's at a dead end. Can't find a solution. Can't go there. Right, and we finally moved our queen off from our very first position, and we start digging around looking for a solution. All right, we haven't even gotten into any mirror cases just yet. Digging for solutions. All right, move the queen down, find a solution, carry on. The thing that makes the problem so costly is just the number of solutions that exist as the board gets bigger and bigger and bigger. Right, dead end. So we've got to backtrack out. And we found another solution. All right, we still haven't got to any mirror scenarios. As you read on this one, you'll differentiate where they'll say total solutions versus distinct solutions, because it just eliminates things that are mirrors. Because let's see, representing this board as a graph. Yeah, effectively, you could probably do that. It kind of looks like kind of an adjacency matrix, but not being used as a matrix in that form. Now we're just using we're just using a matrix, and then from that matrix, just making sure that that's a unique per row column. That part's easy. Then the diagonal is a little bit trickier to test that there's no one on that given diagonal. All right, let's go ahead and take another 5-minute break. Grab another link. That's crap. Queen's links. Yeah, let's take 5. Any questions about the backtracking before we move on to traveling salesperson? Okay. All right, so problem trying to solve here is to find a Hamiltonian circuit on a general or complete graph such that the circuit is the smallest circuit that there is. And so for small graphs, we can get to the solution. But for a graph of size, this quickly becomes an NP scale problem. All right, so looking at a complete graph with 10 vertices,
Professor, what do you mean by NP?
right? Non-polynomial, right? This one,
Oh,
right? So I can go ahead. And a link in there. All right, so starting at some vertex, we have 9 choices for where to go next. There we have 8 choices, then 7, etc., giving us n factorial time or possible paths that we could take. All right, so finding all of those solutions and then taking the best is not practical in the least. So we'll need need to approach it differently. And so one of the things that we can do is create a minimum spanning tree. Spanning tree. And so let's do a small graph. To like 6, let's do like, yeah, that's fine. Yeah, I might be getting a little overzealous here with even 6. It's going to be a lot of edges here. Probably just have to cheat on All right, so finding a minimum spanning tree, of course, we need weights here. Also, we'll just cheat. And arbitrarily choose what it's going to be. All right, so a minimum spanning tree might be something along the lines of this graph. Just need to start blowing things away so we don't have cycles. Still have things connected. That guy there. And okay, there we go. 1, 2, 3, 4. 1, 2, 3, 4, 5. Yep. All right, so there's our, say that's our spanning tree. So what we could do as an upper bound, right? Traverse the path. So we have hit every single vertex, and then reverse course. And we basically set this as an upper bound, getting back to where we started. And then from that point, or if we instead we just create the trail, and then we go ahead and add that line back to where we started, right? So we can start getting upper boundaries on where the solution can be. So as we start trying to figure out what the solution is, we can start making approximations and eliminations. Seeing, right, let's say that the length of this was like 1, 3, 2, 4, and 2 sort of thing. Total path was 6, 10, 12. So as we can start seeing edges that are fairly above average, right? So say like 6. Basically, those are edges that aren't really worth processing. So we can just try to eliminate, do some fuzzy logic type thing, right? We don't really get into fuzzy logic, but the idea behind fuzzy logic is it's a little bit more rough in the numbers. Right? So say you're like looking for, kind of like using 22/7 as an approximation of pi, right? 22/7 is kind of close to pi for, I think it's rational for irrational number, or vice versa. But it's not it, but it's close enough that it's what we'll consider it good enough type thing. You'll see fuzzy logic in like address mapping, right? 123 Main Street might be the true address. If someone posts to 123 Main, we'll be like, okay, that's not Main Street, but they'll have to blank, and we'll go ahead and say that that's going to go to Main Street. But there might also be like, Main Place and Main Boulevard, Main, whole bunch of other things. So depending on how precise we want to be, we can be a little bit fuzzy and saying, yeah, this data seems to match up with that data well enough that we consider it to be equivalent enough for whatever we're trying to do. And that's the sorts of things that we want to do when trying to solve traveling salesman. It's too complex to solve, so we're just going to do concepts. But there are things like the triangular inequality problems, basically make triangles and eliminate long sides and stuff like that. But I haven't looked at that stuff in forever, so I don't recall all the ins and outs myself anymore. We can take some of the approaches we looked at before to try to simplify the problem. Even if it doesn't actually give us the best solution, the solution is close enough to what the ideal or optimal solution is that it's good enough, right? Because You know, it doesn't help to spend 4 years finding the best solution when we're talking about, you know, a 2-month road trip across the United States, right? You're going to get in a car and your objective is to hit the capital of every single state in the continental US. And you're trying to minimize your gas mileage, right? So this the problem is very real. It's the type of things that traveling, because you live somewhere and you're going to come back when you're done with the road trip to where you began. And, you know, once you've been to Sacramento, just because you're close to it, again, on the way back doesn't mean you want to go there again because you've already been there. And of course, in a real world traveling problem, revisiting a vertex would be a very, very likely event because, you know, while you can drive from anywhere to anywhere, you're going to hit places along the way because there's only a finite number of roads and or airways or whatever modes of travel that you're going to exercise between the points in your destination that you're going to work on. That's the general idea. Basically, it's application of a Hamiltonian circuit. One of our other graph concepts we talked about earlier, but that would be it for the graphing section of the course. Any questions about anything we talked about? Probably we'll save till next time. Your brain being already denutrified from the test. Okay, so let's go over the test. Before I start the preview, let me go unlock it. See your answers. Okay, answers are now available. Let's go ahead and stop the recording, please.